The vessel that made every Allied amphibious landing of the Second World War possible was a flat-bottomed boat built from plywood. It was not commissioned by the United States Navy. It was not designed by a credentialed military engineer. The Bureau of Ships spent years working to stop it from existing. Without it, no American soldier reaches the beach at Normandy, no Marine crosses the reef at Tarawa, no landing in the Pacific happens as planned. Dwight Eisenhower said it directly. The man who built this boat won the war. That is not interpretation. Almost nobody today knows his name. To understand why a plywood boat built for Louisiana swamps became the vessel that unlocked every beach in the Pacific, you have to go back to where Andrew Higgins learned to build boats. Not in a naval architecture program, not in a government shipyard. In the bayous of southeastern Louisiana, watching timber boats work water that had no right to be navigable. Andrew Jackson Higgins was born in Columbus, Nebraska in 1886 and arrived in New Orleans in 1910 with no formal engineering credentials and an appetite for problems that conventional thinking had already given up on. He started in the lumber business, moving timber through the shallow inland waterways of Louisiana, the kind of channels where the water was sometimes 18 inches deep and the submerged obstacles were everywhere. The boats available for that work were designed for deeper water. They ran aground. They fouled their propellers on stumps and debris. They were, for the practical purposes of the Louisiana oil and timber industry, inadequate. Higgins did not commission a study. He did not file a report. He built a better boat. The problem he was solving was specific and physical. A conventional hull sat too deep in the water. A conventional propeller, mounted below the keel and fully exposed, was vulnerable to everything on the riverbed. Every submerged stump, every gravel bar, and a conventional bow, designed to push through the water, dug in and dragged when the hull ran over a submerged obstacle at shallow depth. 3 separate problems, each one expensive, each one solvable. The solution Higgins developed over the course of the 1920s and early 1930s became known as the Eureka boat. It had a shallow draft hull that sat high enough in the water to operate in depths where conventional vessels went aground. It had a tunnel stern, a recessed channel running along the underside of the hull at the aft end that sheltered the propeller inside the hull's own structure, protecting it from collision with debris or the riverbed. And it had what Higgins called a spoon bow, a rounded, slightly upturned hull design at the front that allowed the boat to ride up and over submerged obstacles rather than driving into them and stopping. None of these innovations were theoretical. Each one came from watching boats fail in a specific way and building a modification that eliminated the failure. It is a morning in the early 1930s, somewhere on a bayou southeast of New Orleans. The water is brown and absolutely flat, the surface broken by the exposed knees of cypress trees standing in the shallows. A small wooden workboat is moving through the channel at low speed, and Andrew Higgins is watching it from the bank. The bow meets a submerged log. In a conventional hull, this is where the boat stops. The bow drives into the obstacle. The engine strains, the hull shudders. This boat does something different. The spoon bow contacts the log and rides up over it, and the hull slides across the top of the obstruction and keeps moving. The propeller, recessed in its tunnel, never touches bottom. Higgins watches the boat run the obstacle. Then he signals the operator to take it through again. He says nothing. He stands at the water's edge in the morning heat, watching the hull behavior with the particular quality of attention of a man who is checking whether what he has built is actually doing what he designed it to do. It is. He turns and walks back toward the shed. The Eureka boat found a ready market in the Louisiana oil and timber industries through the 1930s. Higgins Industries expanded, building commercial variants for the shallow waterway work that no other manufacturer could reliably supply. By the late 1930s, Higgins had a working factory in New Orleans, a workforce of several hundred, and a design with nearly a decade of operational performance data behind it, accumulated in exactly the terrain that a military landing craft would need to work in: shallow water, obstructed channels, high loads under unreliable conditions, reliable extraction when the engine mattered most. The United States Marine Corps had been developing formal amphibious assault doctrine since the early 1920s. The lesson of Gallipoli in 1915, where inadequate landing craft had left Allied soldiers wading through open surf under fire from prepared coastal defenses, had hardened into a precise operational requirement: a landing vessel capable of crossing a reef or sandbar, running directly onto the beach under its own power, and delivering troops onto dry ground without requiring them to swim or wade the final yards under fire. The distance between where a boat grounded and where a soldier needed to stand was not a logistical inconvenience. In a defended landing, it was where men died. The Navy's Bureau of Ships had its own landing craft in development. It was a vessel designed by credentialed naval architects, working within the established principles of deep-water hull design: a rounded bottom for seakeeping stability, internal troop compartments, and a disembarkation method that offloaded soldiers over the side using cargo nets and ladders. The design had been in development since the early 1930s. refined through successive trials and formal evaluations. In water deep enough for conventional operations, it was adequate. It had been designed in offices, tested under controlled conditions, and refined through institutional channels that moved, as all institutional processes move, at a pace entirely independent of operational urgency. In water shallower than approximately 4 feet, the depth of the reefs and sandbars, guarding almost every Pacific island the Marine Corps would eventually need to assault. It grounded before reaching the beach. Troops went over the side into chest-deep water. They moved slowly. They arrived at the shore exhausted, equipment soaked. Against prepared coastal defenses, that gap between the waterline and dry ground was not a tactical problem. It was a death sentence. The Marine Corps had seen the Eureka boat in demonstrations by the late 1930s, and some officers were paying very close attention. Captain Victor Krulak, a Marine officer who would later become a central figure in post-war amphibious doctrine, attended an early Higgins demonstration in 1939 and reported back with unambiguous clarity. The Higgins design solved problems the Bureau's boat did not. His assessment went up the chain of command. The Bureau of Ships noted it and continued with its existing program. Higgins submitted formal proposals to naval procurement offices in Washington. He sent performance specifications with field data attached. He requested comparative trials in writing more than once. He received no substantive response. The Bureau of Ships already had a design. That design carried the institutional weight of budget allocation, procurement momentum, and years of accumulated engineering investment. Accepting Higgins meant acknowledging that a commercial boat builder from the Louisiana bayous had identified and solved a fundamental operational problem before the Bureau's own engineers had fully defined it. That was not how procurement decisions were made. That was not how institutions acknowledged error. Higgins had the design. He had the performance record. He had officers in the Marine Corps who had seen the boat run reefs and obstacles and written reports saying exactly what it could do. What he did not yet understand was how far the Bureau of Ships was prepared to go to make sure that never changed. The Bureau of Ships did not reject Andrew Higgins because his boat was inferior. The internal documentation from the period makes that clear. The Bureau rejected him because the organization had invested years and considerable appropriations developing its own design, and accepting an outside proposal meant more than changing a specification. It meant admitting that the correct answer had been sitting in a commercial boatyard in New Orleans, while the Bureau's engineers worked on a vessel that couldn't cross a reef. Institutions do not do that willingly. The Bureau's landing craft had been developed through the Navy's standard procurement process, designed by naval architects, testing in controlled conditions, incremental revision, formal evaluation boards. Each step generated paperwork, funding requests, approvals, and a growing body of institutional investment that made reconsidering the fundamentals progressively harder. The program had absorbed years of work and significant naval appropriations. Engineers had been assigned to it, reports had been filed, senior officers had approved successive iterations. By 1940, the Bureau had spent the better part of a decade on a design that still grounded in shallow water. The solution that the people managing the program could see was more refinement, more testing, more revision, more time. Not a different boat. Higgins kept submitting. He sent revised specifications to naval procurement officers throughout 1940 and into 1941. He requested that his Eureka boat be tested alongside the Bureau's design in identical conditions, the same water depth, the same obstacle profile, the same combat load. He asked for nothing more than a direct comparison on the water, where the landing would actually need to happen. The answer, when it came, was always procedural. The Bureau was conducting its own evaluations. The Bureau's process was ongoing. The Bureau declined. It was the Marine Corps that forced the comparison into existence. Unlike the Navy, the Marine Corps had no procurement stake in the Bureau's design. They had not funded it, had not staffed the evaluation boards, and had no institutional reason to prefer one hull over another. What they had was a doctrinal requirement: troops delivered to a beach alive and equipped, and the operational judgment that the Bureau's boat was not meeting it. In 1941, Marine Corps officers formally requested a side-by-side trial. The location selected was a beach at New River, North Carolina, later developed into the facility known as Camp Lejeune. The trial ran over several days in the late summer of 1941. Both boats were put through identical obstacle courses: a shallow bar, a graduated reef approach, and a timed transit from ship to shore with a full combat load. It is late afternoon at New River. The sand is pale and the surf is low, and a Marine Corps officer is standing at the waterline with a clipboard and a watch. Two boats are sitting in the water 50 yards offshore. The Bureau's design rides lower in the chop. The Higgins boat sits higher. The signal goes and both boats accelerate toward the beach. The Bureau's hull hits the sandbar at 30 yards. It grinds, decelerates, stops. Men climb over the gunnels and drop into waist-deep water. They wade the final distance to shore. The Higgins boat crosses the bar without slowing. It runs onto the beach and the bow touches dry sand. The men inside step off directly onto the ground. The officer does not react. He watches the drill run again, a third time. The numbers on his clipboard do not change. He makes a single annotation in the margin of his evaluation sheet and underlines it once. Then he closes the clipboard and walks back up the beach. The formal written evaluation report from the new river trials was unambiguous. The Higgins design outperformed the Bureau's boat on every shallow water metric. It crossed the sandbar. It beached cleanly. It could withdraw under its own power without assistance. The Bureau's design failed on the same obstacles it had been failing on for years. In water shallower than 4 feet, it grounded before the beach. The men had to go over the side. In a competitive trial against a commercial design built for Louisiana bayous by a man with no naval contract, the Bureau's boat had finished second. The result was on the record. The Marine Corps formally recommended adopting the Higgins design. The Bureau of Ships noted the recommendation, filed it, and ordered further studies. But something had shifted permanently. The trial results were now part of the official record, and that record was visible to people outside the Bureau's procurement offices. Admiral Ernest King, who would become Commander-in-Chief of the United States Fleet following the attack on Pearl Harbor in December of 1941, had been closely watching the landing craft question. The Marine Corps' advocacy had moved far enough up the chain of command that the Bureau could no longer manage the Higgins question internally. A contract was coming. Before it arrived, Higgins received a piece of intelligence that changed the boat. In 1941, photographs of a Japanese landing craft, the Daihatsu, reached American military planners through intelligence channels. The Daihatsu had a feature that no American landing craft design had incorporated, a hinged ramp at the bow that dropped directly onto the beach. Soldiers walked off the front of the boat onto dry ground. No netting, no ladders, no wading. The ramp deployed in seconds and created a direct, covered exit from the vessel's interior to the landing surface. Higgins saw the photographs and understood immediately what they meant. The spoon bow of his Eureka design could be modified to carry a ramp without compromising the hull geometry that made the boat work. The tunnel stern, the shallow draft, the structural balance of the vessel, all of it could remain intact. The modification required was structural but not fundamental. He did not request a study period. He did not file a design review. He built a prototype with a bow ramp in 60 days. The new design was tested. The ramp reduced disembarkation time by more than half. Troops could exit in a controlled column at speed, directly onto the surface they needed to reach, under whatever fire was waiting for them. The ramp was the final engineering element that transformed the Eureka boat into a purpose-built assault vessel. It was also something the Bureau of Ships had not thought to include in a decade of development. The contract followed. In the spring and summer of 1941, Higgins Industries received orders from the United States Navy for landing craft built to the modified Higgins design with the bow ramp. The terms came loaded with performance requirements, delivery schedules, and inspection provisions of the kind that procurement offices insert when they want to retain leverage over a supplier they had not originally selected. The order was structured to ensure the Navy could cancel it if Higgins failed to perform on schedule, failed to meet specifications, or failed to meet production targets that had been set not around what Higgins could do, but around what the Navy needed. The contract was real. The quantities were serious. The timeline was not negotiable. He had the order. What he did not have was the factory, the workers, or the time. The Navy needed boats in 18 months. Higgins had never built anything at this scale. Nobody had. The factory Higgins needed did not exist. What existed was a converted furniture manufacturing plant on City Park Avenue in New Orleans, a building designed for assembly lines that produced chairs and tables, not combat vessels. Higgins acquired it, gutted it, and began rebuilding the interior around the dimensions of a landing craft. The problems were immediate and simultaneous. The first was space. The building had to be reconfigured to allow hulls to move through the production sequence without stopping. The second was tooling. The machines that shaped wood for furniture were not the machines that built a marine-grade hull under military specification. The third was workers, and there were thousands of men who had gone to war and left gaps in the industrial workforce that New Orleans could not fill from its existing labor pool alone. Higgins solved all three problems at the same time. It is the morning shift, 1943. The factory floor on City Park Avenue is loud with pneumatic tools and the sharp smell of marine-grade plywood fresh from the stack. Two men are fitting ribs to a hull frame, working in pairs, one on each side, to a template nailed to the floor beneath the skeleton of the boat. One man is white, one man is black. They have been paired on this task for 6 weeks. They do not discuss it. They work the same rhythm. Clamp, check the alignment, drive the fastener, move to the next rib, because the rhythm is what the foreman set, and the foreman is watching the clock. not the color of the men making the joint. Neither man has been told where this boat is going. They have been told the joint must be flush and the fastener must seat clean, because a joint that works loose in salt water is a joint that kills somebody. They make the joint flush, they move to the next one. The integration of Higgins's production floor was not incidental to the scale he achieved. At a time when most industrial employers in the American South maintained segregated workforces as a matter of law and established practice, Higgins Industries put black and white workers on the same production lines, performing the same tasks for the same pay. Higgins did not frame this as a moral position. He framed it as a production decision, and the records of his workforce tell the rest. The labor pool he needed to meet the Navy's production schedule did not exist in sufficient numbers under segregated hiring. The work existed. The workers existed, he hired the workers. Women entered the workforce at Higgins Industries in significant numbers from 1942 onward, taking assembly roles that had no precedent in boat building. By 1943, the company employed more than 20,000 workers across 7 plants in the New Orleans area. Peak production reached a rate of approximately 700 boats per month. One completed landing craft left the line every hour of every working shift. The boats moved through the factory in a sequenced progression. Frame, hull planking, systems installation, inspection, so tightly coordinated that the production floor operated less like a shipyard and more like a controlled river, each stage flowing directly into the next. The Navy had asked for boats in 18 months. Higgins delivered them ahead of schedule. The scale of what Higgins had to build is harder to grasp in isolation. A single Higgins boat required approximately 3,700 board feet of marine-grade plywood, multiple grades of marine hardware, an engine, and the labor of workers whose skills in boat building had to be developed from scratch in many cases, because most of them had never built boats before. Higgins did not wait for workers with the right background. He built the training program directly into the production sequence itself. The first operational test came in November of 1942, when Allied forces landed on the beaches of French North Africa in the operation designated Torch. More than 100 Higgins boats carried American and British assault troops to the shore at multiple landing points along the Moroccan and Algerian coastlines. It was the largest amphibious operation the United States had ever attempted, and it was being executed with equipment that had been in production for less than a year. The conditions were not uniformly favorable. Some beaches were guarded by shore batteries, and French colonial forces responded to the landings with fire. Some approaches were mined. Surf conditions at certain landing points exceeded what the planners had expected. At one location, navigational errors put boats onto the wrong beach entirely, and crews had to reorient and reroute under fire. The Higgins boats performed across all of it. They crossed sandbars, they beached under fire, they retracted under their own power and returned for more men. Not once in the operational reports from Torch was the landing craft identified as the limiting factor at any beach. The limiting factors were navigation, enemy resistance, and surf. The boat did what it was designed to do. The significance of Torch for the Higgins program extended beyond the operational result. Until November 1942, the argument for the Higgins design had rested on trials and theoretical performance data. After Torch, it rested on an actual combat record. The landing craft had been tested against real surf, real mines, real defensive fire, and real operational chaos, and the record showed they had performed. The Navy's procurement decisions from 1943 onward did not require anyone to argue for the Higgins design. The argument had been made at Safi and Fadala and Azu by the boats themselves. 3 months before Torch, in August of 1942, the Pacific had run the same test. When the 1st Marine Division landed on Guadalcanal in the early hours of August 7th, they crossed the reef approaches to the island in Higgins boats. The terrain was precisely what Higgins had spent a decade building for: shallow water, submerged obstructions, variable depth across the final approach. And the boats handled it without reported incident. The Marines reached the beach with their equipment intact and their formation coherent. The initial landing was largely unopposed in its first hours, but the boats had demonstrated under live operational conditions that they could deliver what the doctrine required, in the exact environment the doctrine described. That had never been proven at this scale before. The Axis powers were drawing their own conclusions. German and Japanese military analysts had been tracking Allied amphibious operations, and the assessments reaching their planning staffs identified a landing capability that conventional coastal defense calculations had not accounted for. A boat that could cross a reef, beach directly under fire, and retract independently meant that no coastline guarded by shallow water alone could be considered secure. Every approach that defensive planners had written off as impassable was now a potential assault corridor. Every beach was now a landing site. Every beach had to be held. The stories of the engineers and workers who built the tools that won this war rarely survive the official histories that surround them. If that kind of record matters to you, subscribing is the only way to make sure the next one reaches you, because the landing that would define everything hadn't happened yet. It was being planned in England. and it would require more Higgins boats than had ever been assembled in one place. On the morning of June 6, 1944, the largest amphibious operation in the history of warfare ran on Plywood. More than 1,000 Higgins boats carried the first waves of American soldiers to the beaches of Normandy, to Omaha, to Utah, to the approaches that had been studied and mapped and argued over for months in the planning rooms of southern England. The Channel crossing had been rough. The boats had driven through 4-foot swells, loaded with soldiers who had spent the night sick and cold and waiting. Many of the men in the first waves had never been in combat. Some had never been in a landing craft before that morning. The boat itself made no distinction. It had been designed for exactly this depth, exactly this terrain, exactly this distance between the ship offshore and the beach it needed to reach. The boats that loaded from the transports and drove through the Channel, swelled toward the French coast, were the same boats that had been built on an assembly line in New Orleans by workers who had never built a landing craft before 1942, to a design the United States Navy had spent years trying to prevent from existing. It is 06:30 on June 6, 1944. The interior of the Higgins boat is loud with engine noise and the sound of water against the hull. 36 men are standing in the hold, packs on, rifles up, facing forward. The boat is decelerating. The man at the front can feel it in his legs before he understands what it means. The chain on the ramp goes taut. He does not speak. He tightens his grip on the vertical bar, running up the inside of the forward bulkhead. Next to him, another soldier has closed his eyes. Nobody says anything. The engine drops to idle and the bow touches something, sand or shingle, and the ramp chain clanks once more, and then the whole front of the boat swings down, and the morning comes in all at once. Grey sky, smoke, the sound of everything. The man steps forward. He is the first one off. His boots hit the beach dry. Behind him, 35 more men follow. The operational records of the Normandy landings credited 1,089 Higgins boats to the D-Day assault on June 6 alone. Across the full Overlord operation, the number was larger still. The boats crossed the approaches to 5 beaches under conditions that ranged from manageable to catastrophic. At Utah, where the landing went broadly according to plan, the boats delivered their men onto the wrong section of beach, but the currents that caused the error had also taken them to a less heavily defended stretch of coastline, and the landing succeeded despite the displacement. At Omaha, the situation was different. The Higgins boats continued operating through conditions that should have stopped them. The first waves took the heaviest losses. Subsequent waves still came. The boats ran to the shore, dropped their ramps, and went back for more men, again and again, through an approach littered with bodies and burning wreckage. For hours. The boat itself was not a variable that failed. Dwight Eisenhower was asked, after the war, what single factor he believed had been most decisive in the Allied victory in Europe. His answer was specific, and it was not what the interviewers expected. He named Andrew Higgins. He said that Higgins was the man who won the war for us. A direct attribution, not a rhetorical closing remark, from the officer who had commanded the largest military coalition in history to a boat builder from New Orleans who had held no military rank and received no official credit during the war itself. That is a direct quote. Those words were not widely circulated at the time. Higgins himself was alive when Eisenhower said it. He continued running Higgins Industries after the war, attempting to convert the production capacity he had built for military combat into civilian and commercial applications. Passenger ferries, commercial vessels, the peacetime equivalents of the capacity he had developed. The civilian pivot was not successful at the scale he had achieved in wartime. He died in New Orleans in 1952 at the age of 66, before the full post-war historical record had documented the extent of what his boats had done. The National D-Day Museum, now the National World War II Museum, was built in New Orleans in part because of what Higgins Industries had built there. Its permanent exhibit on Higgins covers in full what most histories of the war leave to a footnote. The total production run of the Higgins boat across the full war years reached approximately 23,000 individual vessels. Those boats were used in every major Allied amphibious operation of the conflict: North Africa, Sicily, Italy, the Pacific Island campaigns, Normandy, and the landings in southern France. No other single vessel type was used across as many operations, in as many different theaters, with as consistent a performance record. There is no major Allied landing that was conducted without them, and no alternative design that could have performed the same function in the same terrain at the scale required. The Bureau of Ships' original design had been retired before 1943. There is a detail about the Higgins boat that is easy to overlook, but that says something important about engineering and the nature of practical problem solving. The boat was not designed for any of the uses that made it essential to the outcome of the war. It was designed for oil workers navigating the Louisiana bayous, for the specific, unglamorous problem of moving equipment through water that was too shallow for the vessels that the established manufacturers could supply. When that problem was solved, the solution did not expire with its original context. The qualities that made the Eureka boat work in the bayous of Louisiana The shallow draft, the tunnel stern, the spoon bow that rode over obstacles rather than driving into them, turned out to be exactly the qualities that a military assault vessel needed, and that a decade of naval engineering investment, carried out by credentialed professionals with full institutional backing, had failed to produce. Good engineering does not know it is going to matter later. It only knows the problem immediately in front of it. That was the case in the Louisiana bayous. It was the case at Omaha. In a photograph taken sometime in 1944, Andrew Higgins is standing on a factory floor in New Orleans, surrounded by the unfinished ribs of wooden boats. He is not in uniform, he never served. He never stood on a beach in the Pacific or felt the ramp go down in the surf off Normandy. What he did was build a flat-bottomed wooden boat for Louisiana oil workers navigating the shallow bayous, and then refused to accept that the United States Navy knew better than he did about what it actually needed. The boat he built from plywood and stubbornness, the boat Eisenhower said won the war, carried more soldiers to more beaches than any other vessel in history. It was a swamp boat. It was also the decisive weapon of the largest war ever fought. The engineers at the Bureau of Ships had better credentials. They had the institutional standing, they had the contract. Andrew Higgins had the boat.